Hi everyone, in this video I would like to talk about stochastic process and train station process and what their difference is and what would happen if you want to run a cointegrating regression model or cointegration model using train station processes. So for this I will create four different time series, so let's create them. So ignore this, these are just preparations. It's creating vectors or series and starting values first, and a loop over 100 observations for the stochastic trend variable, and for the deterministic trend variable just a simple series creation, and then we'll run some simulation later. So let's first simulate this model and then see what happens. So run. Okay, now what I have here is x1t, x2t, which are supposed to be stochastic processes or random walk processes, but this is actually near random walk because it's 0.98, not exact limit, so it's not necessarily a unitary process, but it behaves like a unitary process. These are drifting terms, so one starts at a higher point. Okay, now, and the next, the deterministic trended variables. These are one with drift and one without, just to give them a different sort of behavioral patterns. So let's look at x1. So these are stochastic processes. Actually, I could draw them in one graph together. Okay, new graph, and let's see what they look like. Okay, they do look like random processes or stochastic random walk processes, not necessarily little sort of short process here, and they not much deviating from, they deviate from their pattern. They do not have constant sort of trend, and they do not have sort of constant mean at the same time, except for this one. This more like behaves like a different stationary process, except for this part. So let's simulate this again and simulate another set of variables. Okay, and let's see what happens this time around. What sort of result do we have here? Yeah, this is now more like, again, a train stationary process, but it is not actually, because there's a break in the trend right here in this one. This one more like, yeah, this break from this point onwards to this little flat, while this is very steep pattern. So let's go back again, do one more run, and let's see what happens now. And the graph. Again, well, this looks like, these actually look like more like train station, but they aren't actually. You see, this break in the trend, there's one trend, there's another one at a higher trend. So let's leave them for now. Now, how about this? Two processes. These have to be deterministic trend processes, and here it is, or here they are. As you can see, there is no break in the trend in both of them. It's just they look like more like stationary processes, except that they are actually trending upwards. So that's why we call them trend stationary processes. So this is actually a trend stationary process. Let me write it. Trend stationary process, and this is stochastic trend process. Now, very often we have two series, and what happens is that we usually graph them. Let's start the train station process. Graph them. It's the first stage in your analysis of the time period, and you will be thinking, okay, there is some sort of cointegration between these two. I mean, there is some sort of long-run relationship. Ignore the part about stochastic process, because more often we confuse them. So there is a long-run relationship, and two variables, and I expect at least one cointegrating relation. In other words, linear combination of these two will give me a single stationary process. Now, well, do we need to test for unitlets? You will probably need to. Usually, if you're writing a dissertation, you must write one. You must do one. So let's do a very quick unitlet test. View unitlets, augmented quickly Fuller test. run it usually in levels with intercept selected, no unit root. Sorry, fail to reject the unit root hypothesis, so there is unit root. Yeah, happy with that, I guess. But then choose trend and intercept, because if you don't choose and you conclude at this stage that is unit root, you probably make a mistake, because if you first differentiate, you get a stationary process, because you're now rejecting this at the first difference. However, be careful, always test at levels and always include test for this too, and of course for this as well. But this one is important because we include a trend here, and this is simulation data, and I know that this is a trend stationary process, but you will not know it if it's a real data. So include trend stationary process, but at levels, notice this is levels. And notice what happens. You're rejecting the unit root process in favor of stationarity with a linear trend. Now, this is very important part. Notice the trend term is very significant, highly significant. Next thing is, if you end up thinking or assuming this is a unit root process, you will certainly go and do this. Check the cointegration. And most likely you will leave the default. Oh, there is one cointegrated relationship. So go on and carry on whatever you want to do with the rest. VECM, so run a vector array correcting model. But that would be misleading. I mean, they will get misleading results. First, this is a specification where if your data has stochastic trend, but you know that the data has a deterministic trend. So this has to be the right specification. We have to include restricted trend. In other words, we will have to include trend in the cointegrated regression, because we know from a unit root test that they are trend stationary process, but we conclude them as a unit root. It was incorrect conclusion. In any case, let's run it this way. Intercept and trend in cointegrating equation with two lags. At this, when you chose this option, there was one cointegrating relation, which makes sense in this context because we have clarity, but choose this one now, click OK. Now this makes you confused, yeah? This makes you confused basically, you get confused quickly at this stage because, look, there are two cointegrating relations. And you do this, there's only one. Now what to do now? You're very confused obviously, especially for those who are not experienced well. In that case, given that the test specification is correct, this one is certainly correct because we have trend in it. You shouldn't do cointegrating analysis. At this point, you stop and do not do cointegrating relations because these two series are not stochastically trained, or they do not have stochastic trend. Instead, they have a time frame. So, because you included in the cointegrating relation or cointegrating equation a deterministic trend, it actually strips off the deterministic part, the trend part, and leaves you with a white noise part, in other words, stationary part. When combined, they make up two stationary processes. In other words, if you include two stationary processes in the cointegrated equation, you will have two stationary, sort of long-run relations, basically. They are stationary relations. So you have to be very careful with this time stationary or trend stationary series. So in this case, what's the advice? Usually, books usually give you very nice example with nice results that only give you, single. Usually they limit it to stochastic processes, not time. But in reality, a lot of us get data which are usually time stationary or trend stationary, I should say. In these cases, we have to not first difference the results. It is again another nice way, because we have a trend in your data, we have to remove the trend, and then the result will be stationary process, or result will be the untrended, detrended, I should say, variables can be used to run var. So we have to run var using detrended variables. So what we do now is edit this, usually we have to run regression for that. So let's run this for what was it? YT? Yes, YT. So this code will now run a regression on YT on some constant and some trend. Notice that I'm including constant because I have constant here. So I should have that as well. But usually we won't know, but in any case I can include constant here if the data starts from non-zero value. Now let's run this regression. So it's ls d squares YT y2tc trend, right click, run, select, selected. Now as you can see, this is my result, my trend variable. Coefficient has a very strong, significant, very highly significant coefficient estimate, and C is also highly significant, and I can see serial correlation, and also R squared is high. Now, what next? We have to now create our remove the trend. In fact, this is removed now, but where is the new trend, a new variable, one that we are interested in? In other words, what we are doing is, if I'll go back to origins of what we're talking about. What we wanted was to see if the series are stationary, and with the unit root we know that they are trend stationary now. We also know that we cannot do cointegration analysis. What to do is, if you have two series or maybe three, then if all of them are trend stationary, then we have to run them. We have to put them into var model by detrending them. So I'm now going to detrend the variable. So now what I will do is write a code here. Now let's generate a new variable, generate, and we call it y2tt. So it's detrended, y2dt. Sorry, and this will be equal to what is this? Y2t minus the fitted values. So basically we need the y2t hat here, and the way you write the y2t hat is just this equation here. So this would be constant, so that's 2.4, maybe I'll just copy p plus this times trend. And let's run this. What do we get now? We should get new variable called y2dt. Open this and see graph. Yeah, this is our detrended y2t, y2t. And you could do the same thing with y1t, and it will give you the detrended variables. And then using this y2d and y1t dt, you can do var analysis, so you don't have to do cointegration analysis. It will be misleading if you do it. Right, close it. Yes. Next, we now have stochastic trend process, x12 and x22. Let's open them in groups, and we know they are unit root, or at least near unit roots. We can do unit root analysis, but we don't need to. In the interest of time, we go and do cointegration test. At this stage, we have to decide, we have to make sure that we have the correct test specification. This would be more correct, I would say more reasonable, because we have sort of non-zero starting point. You can say what it is. Basically, we have a different sort of drift turn. In other words, they are drifting up or down. And by looking at the graph as well, you can realize that this is stochastic trend drifting upwards. So it's a positive intercept in there, most likely. But I know it because I included it in the view cointegration. And we would like to restrict it into the cointegration equation. If you and also this is basically unrestricted, I should say, because if you have the intercept in the var as well. So this is unrestricted intercept in cointegration equation and var. This is restricted. It's only limited to the cointegration equation. But go with the third one because the difference of the series will not have zero mean. So okay. Now we have no cointegration relation. This will most likely be the correct result. Have a look. You can, well, maybe incorrect, but we can test it again. So have a look what we have. They're moving upwards, but then we have sort of deviation from trend, and for a long time it won't come back. You see, up to this point they appear to be moving in sort of equilibrium position. While one goes up, the other one goes down. Maybe they have negative correlation, so they have possibility. It's just the way they did behave here is interesting. So what we do now is, let's do a unit root test. Sorry, not unit root test, a cointegration test with just intercept in the cointegration equation, but no intercept involved, and see what happens. Well, in this case we gain at least one cointegration relation. Now, again, you have to be very careful. This is a restricted constant, and that means maybe series when difference have zero mean. So you could conclude the first one or second one. In other words, you could actually stick to the first test where we have this or this. However, most likely you will choose this because it's showing something that you're interested in seeing, which is a one cointegrating relation. Before doing this, what I would do is usually I would first difference the series and see if the mean has a non-zero. If the mean is non-zero. So first thing is let's graph it. Where is the x1 to x1? Let's graph it, and let's do difference. And let's have a look. Where is this graph the first difference? Yeah, it appears the mean is very close to zero. As you can see, it has a mean very close to zero. Now, in that case, the first result. So let me look at the other one. X2t, difference it, and let's have a look at the graph of that. This is also more or less zero mean process, almost zero mean process. In that case, let me go back to option, second option. Actually, this is open. In this case, second option, this option would be fine because the mean is almost zero in the difference terms. So when we first difference, so this would be the more or less correct decision, and we could run the VECM. However, notice that we're looking at the bivariate case. We could actually have angle gradient. Angle gradient is two-step process as well here because it's bivariate, and there is not much more than one cointegrating relation. But maybe you have some sort of structural modeling in mind, then you run VECM, certainly. Okay, so this basically hopefully will help you in deciding what to do with the train station range stochastic variables. And hopefully you'll leave comments on how to improve this, or anything that you think that is misleading or has something wrong with it, or you want to comment and we'll work through that. Okay, see you later in the next video.